All right, so guys, section 4.7, inverse trigonometric functions. All right, so good news here is that I don't know, I'm assuming good news. I should be clear about that. Is that maybe not everybody? This is taking forever. Should I be nervous about this? Not showing up? Do you have to say like pretty please or? There we go. There we go. It was the pretty please, I think. Yeah. So anyway, so back to this. Again, today's kind of a lost day. Where was I at? No. With being what I'm assuming is a little bit of good news is that we're going to be looking at graphs today, but we're not actually graphing. Okay. So again, I know that throughout really the entire week, actually even going back to last week on Friday, since last week on Friday. Monday, Tuesday, Wednesday, it's been all about graphing. And again, I think that I don't have to stress it any further. We know that graphing our 6 trig functions is going to be a big part of what we're doing next week on our test and things like that. That's going to be a big aspect of it. But that's not everything. There's other things in chapter 4 besides the ability to sketch the graph. So again, kind of going along with the question it was asked earlier about, like, well, when do we use the sine curve? When do we use, like, we're actually going to use it to better understand the idea of inverse. So the good news about inverse, like, we've actually already used inverse trig functions in this class, you know, actually even a little bit this semester, quite a bit last semester. But these are concepts, inverse trig functions. This is stuff that you learned in geometry. You used it there, you used it last year in Algebra 2. Typically, it would have looked something like this. This is what we probably feel most confident or comfortable with. We would use inverse trig functions to find angles. So again, with our knowledge of SOHCAHTOA, again, we know that sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent, and we could use any of those three because we have all 3 pieces here, meaning opposite, adjacent, and hypotenuse. We could use whichever one we want to find the measure of that angle. So Campbell, you get to pick. Which one do you want to use? Sine, cosine, or tangent? Tangent. All right, so Campbell says he wants to use tangent. Just for the record, we could have literally said sine, cosine. And I don't know, I didn't intend to be misleading, I suppose, but we could have also gone with cosecant, secant, or cotangent, for that matter. But again, we're going to roll with tangent here. We know that tangent's opposite over adjacent. So do we all agree that from theta being marked where it is, the opposite is 5, the adjacent is 12? So everybody's good with that equation that I'm writing up, that the tangent of theta is equal to 5/12. Now, what we're going to have to pull off here is that I don't want the tangent of theta, I want theta by itself. So I wanted to give myself a little bit more space here, that would have been smart. So if I'm looking at this equation, I guess the big question becomes, how do I eliminate or get rid of tangent? What do I have to apply? Tangent inverse, right? So if I apply the tangent inverse, the catch is that if you do it on the left, you do it on the right. Now I'm not doing anything that you haven't seen a million times, but tangent inverse, they will eliminate, they'll cancel one another out, leaving us with theta is equal to the tangent inverse of 5/12. Then we get theta's, as my memory serving me correctly, about approximately 22.6 degrees. Now, if your calculator's in radian mode, you'd get the angle in radians, which is fine, but 22.6 degrees. Now, a question for you real quick. Your calculator, by the way, did everybody's calculator give them 22.6 degrees? It wasn't like some calculator said 157.4 degrees or anything like that. So unanimously across the board, everybody's calculator says 22.6 degrees. Okay? All right, good job focusing on the wrong part. Yeah, okay, but anyway. So we're all in agreement that everybody's calculator says this. Now, here's the deal. What if this were in the coordinate plane? The way that I have that sketched, in the coordinate plane, it kind of looks like that'd be in the second quadrant. Okay. What if I sketched it this way? This is the way I think that we all naturally kind of work with it. That's 5, 12, 13. That's our 22.6 degree angle right there. Over here is merely a reference angle of 22.6 degrees. It's still the same. But wouldn't the actual measure have been different here? Like I said, of 157.4 degrees, something like that. So again, going back to it, how did your calculator know that you wanted to be in the first quadrant, not the second quadrant? Again, the difference here would have been, adjacent would have been negative if we were in the second quadrant. So again, how does your calculator know which to go with? Because everybody's calculator said the same thing. How do we do that? So the fact of the matter is that your calculator has been programmed a specific way, and we're going to now try in section 4.7 to program your brains, frankly, because honestly, if we're asking where could you draw a triangle such that the tangent is positive 5/12. Actually, I drew it falsely here. It wouldn't really go in the second quadrant then. But again, what if we switch this up to the sign, the way that I drew it? If we're talking about the sign, where could we draw a sign of positive 5/13? We could have drawn it in the first quadrant or the second quadrant. Okay. What if we had a cosine of 12/13? Something like that. Well, wouldn't that have been possible in quadrant 1 or quadrant 4? Okay, the cosine would have been positive in both of those cases. So again, kind of meshing that concept of all students take classes. Where are our trig functions positive? Where are they negative? Basically, every one of these options, again, if we would have talked about any triangle, you could have put, again, or every trig function of a triangle, you could have drawn it here, or you could have drawn it there. You could have drawn it here, or you could have drawn it in that other. And then now all of a sudden we have an argument on our hands. What's consistent? What's the norm? So that's what, like I said, your calculator's been programmed that way. We just need to turn your brain into a situations where we're using that same concept. All right? So the goals that we have in mind over, like I said, today and tomorrow, students be able to evaluate and graph the inverse trig functions. Again, we are not going to be drawing the graphs. We're going to use the graphs like, hey, look at that picture, and then go over here and do something with it. We're going to do that, but we're not physically going to be graphing these inverses much at all. And then number 2, students be able to evaluate the compositions of trig functions. That'll definitely be a tomorrow thing. All right, guys, here's kind of what it boils down to. Just out of curiosity, how many of us have seen this notation or this that term of arc sine? Does that look familiar? A couple of us have seen it. Okay. I know that we've all seen sine inverse. Maybe we haven't seen arc sine, but they mean the exact same thing. Okay, our arc notation and our inverse notation, just different ways of saying this. It's kind of like, even though it's physically looks the same, if you were to see this, some people are going to say square root x, some people are going to say radical x, some people are going to say root x. They all mean the same thing. All right, so same deal goes here. Arc sine and sine inverse, one and the same. Some of you may even have calculators that it says arc sine, arc cosine, arc tangent, and that's great. Again, it just means sine inverse, cosine inverse, tangent inverse. Exactly the same thing. All right, so when we, first semester, talked about inverses, and we did it multiple times in different chapters, whenever we were calculating and using inverses, wouldn't you agree that inverse really means that we're going to switch x's and y's? Like, ultimately, that was the big deal. So when we were solving with inverses algebraically, we would literally look at a function, take the x's and the y's, and we'd flip. Wherever there was an x, we'd make it a y. Wherever there was a y, we'd make it an x. And then we would solve for y. That's how we found the inverse. Okay, so that isn't changing. That's still going to be the same here. So if we were to think about the inverse sign, graphically, that's going to be a little weird. All right, so I think that it's going to work best if we just show a visual here. All right, does everybody agree that that is a graph of the sine curve? Going through the origin. Again, yep, looks like that. So if we change all of the x's and the y's, basically what's going to happen, it's going to turn into, okay, that's the sine inverse curve. Does anybody notice a problem with that, though? That's not a function. Why is that not a function? It fails the vertical line test. So that, in and of itself, that's the problem. Okay? Now, how does that relate back to what we're trying to talk about? That relates back because when I ask you to, okay, go ahead and draw the triangle that has the sine of 5/13, and a bunch of you draw it in the first quadrant, and then a few people draw it in the second quadrant. Now all of a sudden I have to be like, oh, hey, sorry, second quadrant people, you're wrong. Well, you're not really wrong. You are, but you're not. Does that make sense? Like, it's because all of a sudden we're running into some issues and some problems like this. Okay? So what happens, and it's going to feel like we're cheating here, but what we are going to do is we're going to say, oh yeah, that's like the entire sine inverse, but we're just going to go from here. That's all that we're actually going to use. Does that pass the vertical line test? Just the highlighted blue portion? Yeah, so instead of saying that we're cheating and we're cutting all this stuff off, we're going to use fancy talk like we're going to create restrictions is what it is, right? It's still cheating. Now, guys, we do this all the time. We've been doing this for quite a while. Think back to, again, the quadratic. F of x, f of x. Jeez, please. Let me try this again. F of x equals x squared. We know what that's going to look like, okay? That parabola. Technically, wouldn't the inverse technically look like that? That doesn't pass the vertical line test, so what do? What do we know the inverse of squaring is? Square rooting, and that's why our square root function just looks like that. Okay? I know we talked about that, like I said, first semester, but we've been using this trick for a while. And it's not just exclusive to squaring, square rooting, or inverse stuff at all. So when we're looking at a sine curve, we know that the sine curve has a domain from negative to positive infinity. Well, as soon as we, and then also the range is from -1 to +1. Well, as soon as we look at the inverse, its domain is now from negative to +1, but the range, that's where we have to cheat. We're going to say, yep, it's just going to be from -π/2 to +π/2. Okay? So let's think about quadrants now. Where is that? We're going to talk about this a lot more. Again, think about that unit circle. Where's -π/2? Is that down here? Where's +π/2? It's up there. So we're saying that we could be allowed in that vicinity. When I say vicinity, that means we're in quadrant 1 or we're in quadrant 4. Now, if we're talking about sine, all students take classes. Do we agree that sine is positive? Sine here. Sine is positive there and it's negative there. So what if we try to say, well, isn't sine positive in the second quadrant? Yeah, but that's off limits. Third quadrant, it's negative. Yeah, but that's off limits. Okay? So for our purposes, if we're talking about sine inverse, you're down to 2 quadrants. If it's positive, you're in the first. If you're negative, you're in the fourth. But we're going to be able to do the same with cosine and tangent. Cosine is going to be a little bit different because if I try to use quadrants 1 and 4 for cosine, isn't cosine positive in both 1 and 4? So we can't do that. We're actually going to use 1 and 2 for cosine. 1 and 2. Positive in 1, negative in 2. Tangent, we're just like sine. We're going to use 1 and 4, positive in 1, negative in 4. Okay? So a lot more to come on this tomorrow, but the big takeaway in these last seconds that we have is that if you're using the arc or the inverse notation, you're finding angles. That's what this is about, is what angle on the unit circle leads to whatever we're asking. Have a good day, guys.